We pretty much take for granted that the things we wear, the things we live with, those things with which we play, and the things we work with, that all these things come in colors. Colors to be had in every imaginable shade, and colors that will not fade or run or come off on our hands. In fact, we've come to take this so much for granted, many of us do not stop to realize that it presents any problem at all. Yet the study of color and light is a science in itself, a science that helps us to understand the appearance of everything around us, from feathers to flowers, from foliage to fire, and from fire to the firmament, the gallery where one of nature's earliest forms of art still hangs, the rainbow. Raindrops hanging in the air separate all the colors in sunlight. This is called a spectrum. And this is the same thing man-made, the glass prism taking the place of the raindrops. But both the man-made prism and the heavenly rainbow tell us the most important basic fact in the study of color, that there is no color without light. So that the color of the screen before you seems to depend entirely upon the color of light cast upon it, starting with violet and going to blue, green, yellow, orange, and red. But is the color of the light the whole answer to the way an object looks? Not entirely. For here is a scene under one kind of white light, and here is the identical scene under another kind of light, but whose whiteness is the same as the first. Here the scene changes in depth and intensity as we move the light. And here the figures appear first shiny, then dull, yet without changing color. So that in order for us to see a color, we need first a source of light, which may be anything from daylight to an incandescent lamp. It is the color of this light that reaches our eye, but it is modified by the object it falls upon or passes through. It may be modified by falling upon foliage, or rocks, or the earth, or by passing through water or glass, or the atmosphere itself. Each color in the spectrum has its own individual wavelength, just as each note on the piano has its own sound or wavelength. However, you can't play all the notes on the piano at the same time and arrive at anything. But you can take the basic colors of the spectrum and arrive at pure white. From these 5 principal colors come thousands of combinations and variations, shades and hues, all appearing differently under different conditions of light and pigment. Yet that part of the spectrum visible to the human eye comprises only this much of the entire electromagnetic spectrum. That is, of all the forms of electromagnetic energy shown on this chart, these are the only ones we can actually see. We cannot see radio waves, X-rays, radar waves, ultraviolet waves, or any of the others. These wavelengths range from the extremely short ones of X-rays and gamma rays, with wavelengths of a millionth of an inch, to those of the longest radio waves, some of 100 miles and more. However, despite their extraordinary shortness, wavelengths of light can be measured more accurately than any other physical quantity, and this has enabled us to make some headway in the complex study of light and color. As we can see, violet at the one end has the shortest wavelength, while red at the other end of the spectrum has the longest wavelength. We know that all electromagnetic waves, including light waves, travel at the enormous speed of 186,000 miles per second. Let's slow this down a bit so we can see what's happening. But let's keep on assuming the beam is still traveling at that tremendous rate, and in a vacuum or in free space. Because when it suddenly has to pass at an angle into a transparent material, like water, the direction of the beam is changed, like this, since it is slowed down considerably by the denser medium, so that the light beam is actually bent or refracted when passing from one medium into another. And this is why an object seems to bend when placed in water. Its direction seems to be altered. The lines on a printed page appear to be in a different place when seen through a piece of glass like this. But the bending, or slowing down, is different in this medium. The amount of bending or slowing down is called the refractive index of the given material. Yet this isn't all that takes place. We also get a reflection of a portion of the beam. This happens whenever there is a change in index from one material to another, in this case, from the air to the glass. Here, with ordinary glass, approximately 4% of the original beam is reflected from the surface. That is, the light is reflected in one direction, like this, but only when the surface is smooth or glossy. When the surface is rough, however, the reflected light is scattered in all directions because it is hitting that many more individual surface angles. It is this understanding of the basic behavior of light when it hits an object that underlies all our knowledge of industrial finishes, lacquers, textile colors, printing inks, and all forms of chemical coatings in art and industry. These materials are all basically composed of a vehicle, or liquid, in which are suspended innumerable fine particles of an insoluble substance, sometimes called a pigment. Let's say our vehicle is linseed oil, and our pigment particles are made of the same glass we have seen, ground into a fine powder. We now have the ingredients for a basic form of chemical coating, that is, a vehicle in which pigment particles are suspended. The coating can now be applied to a surface in a thin layer, as we do with paint, for instance. But the story only begins here. Since linseed oil has a different refractive index from air, the beam of light acts the same way as it does when it hits a sheet of glass. A percentage of the light is reflected at the boundary surface between the air and the film of linseed oil. Now let's see what effect the pigment itself has upon the light that enters the film, in this case the ground glass. If the type of ground glass has the same refractive index as the linseed oil, there will be reflection at none of the pigment surfaces. In other words, the light will pass through the film as if there were no pigment present, until it strikes the surface on which the film has been coated. If this surface is white, virtually all the light will then be reflected back through the film into the air. If the surface is black, practically none of the light will be reflected. In either case, this coating, or paint, or film is transparent, since the light passing first in, then reflected back out of it, is not reflected in any other directions by the pigment particles. Actually, in both these cases, since the insoluble glass particles are transparent, ordinarily we would not call them a pigment, but rather an extender. But if the type of ground glass used as the pigment has a different refractive index than the vehicle, you will remember that reflection will take place wherever the light strikes an individual particle. So that if there are sufficient particles, and if the film or coating is sufficiently thick, virtually all of the light will be reflected before it has a chance to penetrate down to the surface. In other words, we do not see the surface at all, and we then have an opaque coating. So we have seen that a beam of light is bent when it enters a transparent material. But the amount it is bent depends also on its color or wavelength. A prism inserted in a beam of white light not only bends the beam, but bends each color to a different degree, giving us the familiar spectrum. The index of glass being highest for violet light and lowest for red, we can see then that the violet is bent at the greatest angle, while the red at the other end is bent the least. We also find that there is a difference in the intensity of the individual colors, depending on what kind of light is passing through the prism. In the case of an ideal white light, all the colors would be equally intense. With light from the sky, these colors are more intense. And the spectrum of light from a tungsten lamp results in these colors being the more intense. Here is a colored material, a sheet of red glass. It will be easier to understand the behavior of the light now if we think of it as composed of the spectral colors, which are actually inherent in it. What is happening here indicates that the transparent red material has the property of absorbing all the colors of the spectrum except red, which it allows to pass through. The yellow glass completely absorbs violet and blue, but it transmits red and also its own color, as well as to a lesser degree the color green. A green transparent material will of course transmit its own color, along with this much yellow and this much blue, but will absorb the colors at both ends of the spectrum. Blue glass absorbs yellow and red and transmits violet, blue, and green in these proportions. Magenta glass absorbs green and transmits violet, blue, yellow, and red in these proportions. Fortunately, what we have just seen can be expressed far more accurately in terms of graphs, which reveal color differences the eye could never see. Later, we will show how this ability to define any color really accurately and any shade of that color is of immense importance to all of industry. This instrument, the spectrophotometer, can measure precisely the amount of light absorbed by a given material at all points in the spectrum, and the amount of light which will be transmitted. The whole concept of mass production, in fact, would be impossible if we could not control the matching of the coloring materials used in practically all phases of our everyday life, and if we did not understand this process of selective absorption. For now we know that the pigments in these coatings produce the effect of color in the same way as the colored glass. They are absorbing some colors selectively and transmitting others. And they are acting in the same way as did the transparent ground glass suspended in a transparent vehicle. In fact, let us think of this pigment as red glass, finely ground and incorporated in a similar transparent vehicle, the same red glass through which we passed a beam of light a moment ago. Although this beam appears to the eye as white light, we now realize that it is actually composed of the 5 basic spectral colors. We will see that each of the ground particles of red glass acts in the same way as when they were all together and forming a solid sheet of red glass. In other words, each particle has the property of transmitting red rays freely and of absorbing all other rays. That is, all the colors but the red will be absorbed by the red particles, and only the red rays will be able to penetrate downward through the transparent vehicle. Now, if, as we have shown, the pigment has the same refractive index as the vehicle, no reflection will take place. This means that the red rays will continue unobstructed and undeviated until they strike the surface on which the film has been spread. If that surface is white, the red rays will bounce back up through the film again and into the air, and we will have a transparent red. If, however, the refractive index of the pigment is not the same as that of the vehicle, and if there are enough particles, all of the original red beam will be reflected before it has had a chance to reach down to the surface. This film will be opaque, and the original color of the surface, white, will have no bearing on the color the eye would see, red. Now let's see what happens when we mix colored inks. The color yellow is first printed on a white page. Then, on top of it, a blue-green color, cyan blue. Most people assume that blue-green and yellow will make green. But actually, since no color can be made where it didn't exist before, it is more accurate to say these two colors leave green. In other words, the green was not produced by magic. There was some green in the yellow to begin with, and some in the blue-green, or cyan. But now, how can we tell what kind of green we will get? Can we be sure if we will get this green, or this, or this, or this? This happens to be the right green for this particular blue-green and this particular yellow. But the point is, we can accurately predict which green it will be out of the thousands of different kinds of green there are by means of the reflectance curves for the original blue, green, and yellow. First, let us find out what is happening. As we have seen, the cyan ink will absorb the yellow and the red rays before they reach the yellow ink, but it will transmit the violet, the blue, and the green rays. The yellow ink, however, will, as we know, absorb the violet and the blue rays, transmitting only the green rays, that is, allowing them to strike the white surface of the paper and bounce back up into the air. What we finally see then is the color green where the blue and yellow inks overlap. And we can tell exactly what shade of green it will be by translating this information into the form of a graph. Here's the reflectance curve for the blue-green ink. And here's the reflectance curve for the yellow. Obviously, we can see at a glance where in the spectrum we are going to come out. Green. And from the curves for the cyan and the yellow, we can compute the curve for the green, which will result from the two. Arriving at this third color as a result of overlapping, or mixing the other two, as in color printing, is called subtractive mixing, for the simple reason that the second color, the cyan, cannot add anything to the yellow color under it, but can only subtract or absorb rays from the beam of light, in this case, the red and yellow rays. Thus, in color printing, 2, 3, and 4 colors are put on top of one another to get reproductions of an original painting or color photograph. Generally, though, the pigments are mixed beforehand, as in the original painting, then applied directly to a surface. Nevertheless, if the pigments are transparent, the color of the mixture can be accurately predicted by the reflectance curves of the colors to be mixed, for when light strikes the pigments, it follows the same rules as it did with the two inks we just saw. The processes of absorption, transmission, and reflectance are carried on just as with the dry inks, and the green we get can be predicted with just as much accuracy. Without this knowledge, this ability to know exactly how to determine and how to arrive at a desired color, not once, but thousands and thousands of times over, without this knowledge, virtually everything we have about us, from our clothes to our food packages, would look strange indeed. In fact, it becomes increasingly obvious the more we learn about the mysteries of color that modern production methods must lean heavily on the scientific control of pigments, dyes, and inks. So far, we have only considered subtractive color mixture, that is, where certain colors are filtered out, leaving others. What we are going to see now, however, is something else again, additive color mixture. Here is a pattern composed of alternating blue and yellow squares. But seen at a distance, where the eye can no longer distinguish the individual squares, we find that the two colors blend or mix. They blend in the eye, however, and not into the green we would expect by mixing two paints of these colors, but rather into a light gray. This too can be predicted by taking an average of the reflectance curves for the two colors. The curve we get from this average of the other two curves indicates a gray because of its flatness, meaning, as we can see, that it is neither high nor low at any particular wavelength, but is about the same for all. Here is another way of demonstrating additive color mixture, the Maxwell disc. The colors are rotated until again the eye can no longer distinguish them separately and sees only their mixture, which turns out to be the same gray as with the squares of blue and yellow. In general, artists use the subtractive method by mixing their colors before applying them to a surface. But there is one school of painting which utilizes additive mixture. The French impressionist Seurat was the first modern painter to make use of the technique of pointillism, which is nothing more than the laying on of small, individual dots of paint, which, when juxtaposed in the mass, blend together in exactly the same manner as the blue and yellow squares did. But in this case, their colors were selected to produce an extremely lifelike effect. And a far cry from the 19th century French painting, it is interesting to note that today, the most up-to-date commercial application of additive mixture occurs in the most modern art form, color television, where the same principles hold. When we saw the yellow and blue squares a moment ago, we thought they would result in green. But by additive mixture, it turned out to be gray. And here, on color television, we find that it is red and green, which add up to being yellow. Now, as the scene changes on the television screen, let's see what new color red, blue, and green will give us. White, of all things. Now for a further complication. Let us suppose this object were to be televised. First, let us see the curve for this particular color. Very well. Now, here is the same object as it would appear when color televised. It looks to the eye to be the same as before, yet look at its curve now. Strangely enough, although the colors of the object appeared to be the same when seen with the naked eye as when seen on color television, the curves for each are quite different. The explanation? It comes down to this: the human eye and how it sees. Another whole new field, and one we haven't time even to begin exploring in this film. We have found, however, that color is not an intrinsic property of physical objects, but depends to an equal or greater extent on different kinds of light and on the nature of the human eye. We have seen something of the behavior of color and light. Refraction, reflection, transparency, opacity, subtractive mixture, additive mixture. And we know this is a field for scientists and technicians, the people who have learned to control and manufacture coatings and coloring agents, printing inks, varnishes, lacquers, dyes, finishes, and textile colorings, to help beautify everything around us, wherever the eye falls, and to make that beauty permanent.